Hello, everybody. My name is Victor Blisk. I was asked by the colloquium committee to this is but I worked at full center for physics and participant of the workshop quantum matter through the labs of Moiré materials that is very good use Feldman of Stanford University. So Ben is an expert of dimensional materials, correlated matter in PhD, etc. So he got this PhD working with Amir Yacoby at Harvard, and then he was a postdoc with Ali Yazdani at Princeton, and since 2018, I believe, he has faculty at Stanford. Today, we'll be telling us about unveiling the microscopic magic of fluoride materials.
All right. So thank you very much for the kind introduction and for the opportunity to give a colloquium. It's been a really nice workshop so far. I've enjoyed talking to folks both in the Moiré materials workshop and also meeting folks outside the field. So what I hope to do today is give a little bit of a perspective on some recent work that I've been involved in, looking at these sorts of Moiré materials where you take dimensional systems, stack them often with a small interlayer twist. And this is a recipe for giving rise to new types of quantum phases of matter. And so I'll try and provide some insight into what sorts of different kinds of phases can be realized and what is it microscopically which controls what phase appears in which portion of a particular phase diagram. So let me start just by acknowledging the people who were involved in this work. So this was primarily carried out by three graduate students, excellent graduate students. Jiachen Yu and Carlos Cometer worked together on the first thing that I'll talk about, and then Ben Foudy together with Carlos Cometer the second material system that I'll describe, and had a number of really wonderful, insightful theoretical discussions with Liang Fu and his group at MIT. Tritep Devakul in particular was a postdoc with Liang when things started out, and then he interviewed at Stanford and really launched actually a lot of the collaborations that I'll tell you about, and was the glue for all of this, and now he's a faculty member, a colleague of mine at Stanford. Where I'd like to start is simply just from reminding you of atomic orbitals. And when you take these atomic orbitals and you arrange atoms in a particular periodic lattice, any number of different kinds of lattices, then these orbitals sitting on individual atoms will hybridize with one another. And as a result of that hybridization, the electrons that are moving through these materials require some sort of kinetic energy. There's some dispersion, that is, there's some energy of a particular electronic state, which depends on its momentum. And for a long time, and in many, many cases, actually, all you need to do to understand the properties of a particular material is ask the question, what does a single electron do as it's moving through this lattice of atoms connected through these different atomic orbitals? And okay, you have some elements, some atoms, they have some electrons associated with them, and you fill up from the bottom these bands until you've exhausted all the electrons that are available in your system. And the electronic properties of the material are really dictated by where you end up. So if you end up in your Fermi level, that is the highest occupied electronic state, cuts through the middle of a band, then generally you get a metal. If, on the other hand, Fermi level, you've completely filled up all of these bands and there's some energy gap to the next available electronic state, and you have an insulator or a semiconductor, depending on the size of this gap. So this is a picture for silicon. This framework is tremendously powerful, describes copper really well, describes silicon, has obviously important implications for materials as we know them. But actually, in this talk, I'd like to highlight instances where this simple picture breaks down. So I'll highlight a couple of examples. One is when you have strong electron-electron interaction. So traditionally, there are assortment of strongly correlated materials where electron-electron interactions are actually more important than this kinetic energy associated with the band structure of the material. And a very simple but powerful model to look at, in some contexts at least, the role of electronic interactions in these materials is this Hubbard model that I'm showing here. Oops, I've got my mouse in the middle of things. Somebody else's mouse in the middle of things. Mine. Anyway, so this Hubbard model is very simple. It's described by two parameters, U and T. U is an on-site repulsion. That is, if you have a particular site of the lattice and it's occupied by two electrons, then they experience some Coulomb repulsion, which is parameterized by U. And there's some probability T for an electron to hop from one lattice site to the other lattice site. And these two properties or parameters dictate the behavior of the system. That is, if you are in the limit where the interaction energy U is small compared to the hopping strength T, then you put your Fermi level right in the middle of your band. That's a metal, just as you'd expect from the single particle limit. But on the other hand, as you crank up the strength of interactions such that U is large compared to T, then put your Fermi level right in the middle of this band, then actually a band gap opens up as a result of the interactions. That is, if you fill your system, have one electron per site in your system, these electrons can't hop from site to site because of this energy cost U. And so you split up into what's known as a lower Hubbard band, an upper Hubbard band, and you get an extra energy gap in the system, and it acts like an insulator, even though naively you might have expected it to be a metal. These are short-range interactions. These are on-site U's that I'm talking about. Of course, electrons interact by Coulomb interaction. This is the long-range interaction. And so you can also get this transition from, say, itinerant or delocalized electrons or metallic behavior in the low non-interacting case. So you might have some liquid electronic state. And if long-range interactions are strong enough, then actually want to spontaneously form some sort of electron solid known as a Wigner crystal, where the electrons mutually repel one another and sit as far apart from one another as possible. And this forms what's known as an electron solid. That is, you have this periodic arrangement of electrons in your system. The other example where this simple single electron physics breaks down is in the context of topological physics of matter and material. And so the probably best known experimental example of these topological phases comes from the quantum Hall effect. So when you have a two-dimensional electron gas, your electrons are confined to 2D, and you apply a large magnetic field. The energy spectrum looks like that of a quantum harmonic oscillator. So it breaks up into these discrete levels known as Landau levels that are highly degenerate. There are many, many electrons undergoing cyclotron motion. And when you put your Fermi level somewhere in between these Landau levels here, and what ends up happening is the bulk is insulating. You have chiral edge modes which are going around your sample. So the insulator that you get in this quantum Hall system is distinct from the trivial insulator that you get, say, in silicon. And this has some interesting transport quantities consequences as well. That is, when you have your Fermi level between these Landau levels, you have zeros in your longitudinal resistance. If you measure resistance along the direction of current flow, it vanishes, and there are corresponding plateaus in the Hall resistance transverse to the direction of current flow. And generically speaking, these topological systems have some sort of quantized response, which is associated with. This is back from the 1980s. More recently, it's been realized that, in fact, there are materials that intrinsically can be topological without needing to apply a magnetic field. So, for example, you can have a quantum spin Hall insulator where, again, the bulk is insulating, but you get some band inversion such that as you go from this insulating bulk to the vacuum outside the material, again, you have to have some low energy edge modes. And now in this quantum spin Hall system, depending on which spin your carrier has, you move in an opposite direction. So this is a situation where you have time reversal symmetry, whereas it's broken, obviously, in a magnetic field. Finally, if you have something like a quantum spin Hall system and you induce some magnetization, either by dopant atoms or intrinsic to the material, then what you can do is you can actually realize a chiral mode goes around. Again, you have some insulating bulk, but now you can realize this at zero magnetic field. This is known as the quantum anomalous Hall effect. Anomalous because it occurs at zero magnetic field. You don't have to explicitly break time reversal symmetry with this applied field. Okay, so these few kind of counterexamples of the simple single particle single particle picture really make up a lot of the most interesting systems that we as condensed matter physicists really like to study. So in the case of electronic interactions, I already talked about strongly correlated materials. These are, well, there's various classes of them. For example, high temperature superconductors. In general, in addition to this insulating phase that I described, when you have a half-filled Hubbard lattice, you can get superconductivity, you can get various forms of magnetism. There are many, many other phases that appear in this phase diagram, and still to this day, even after decades of study, we don't have a complete picture of why this, what exactly is governing this behavior and how to understand. And so, of course, there are also examples at the intersection of this, so I'll come back to these toward the end of my talk. But in general, if the title of this workshop that I'm sort of trying to represent here is quantum matter through the lens of Moiré materials, well, quantum matter part is what I'm showing here, that when you have strong electron interactions and non-trivial topology, you can get interesting quantum phases of matter. Well, unfortunately, usually the materials that you need in order to realize these are very complex. They have many, many atoms, they have many, many orbitals, and that makes them hard to understand theoretically and also tend to be very hard to work with. So what we'd like to have, instead of being governed by the tyranny of chemistry, how do these different atoms like to bond together with one another, it'd be nice if we could have some sort of simpler system we can use to give rise to these same sorts of phenomena, but now in a more controlled fashion. So luckily, yes, almost 20 years ago now, I'm old, it was realized that you don't necessarily need to start from three-dimensional materials. That is, there are certain materials which are known as van der Waals materials that are layered, and within an layer, there are strong covalent bonds, but between layers, bonds are fairly weak. And so what that means is all you have to do, and this was discovered by Andrei Geim and Kostya Novoselov back in 2004, all you need to do is take a piece of Scotch tape, brand name works really, really well, put it on some chunk of graphite, peel it off, press it onto a silicon wafer. You can look through an optical microscope and you get a picture that looks like this. So this is actually from my PhD days. And as PhD goes, this is etched in my memory. You can tell from the optical contrast exactly how many layers you have. So the thinnest thing, so this background here is just the silicon dioxide wafer that we've posited this thin flakes on. The thinnest thing that you can see, the faintest thing that you can see over here is monolayer graphene. This is bilayer graphene, so it's two sheets of carbon atoms stacked on top of one another. This is much, much thicker graphite. Exactly how thick, I don't know. You can really tell the difference, 1, 2, 3 layers, so on and so forth, just looking through an optical microscope. And graphene's not the only material. So since its discovery, turns out lots of van der Waals materials that each have their own individual properties and are amenable to the same sort of Scotch tape technique where you can isolate them layer by layer. Any kind of property you can imagine in a three-dimensional material, I would posit that actually exists in a two-dimensional material as well. You have insulators like hexagonal boron nitride, which is very much like graphene, except it's insulating. You have semiconductors like molybdenum diselenide. I'll talk about similar materials throughout this talk. You can get superconductors like niobium diselenide, you can get magnets, you can get topological materials, and so on and so forth. And the nice thing about these different material systems is that you can mix and match them. So again, unlike these conventional materials, these three-dimensional systems, where you're really limited by the chemistry of how atoms like to bond in the third axis, now you can stack individual layers however you like, though they were Lego. Now, actually, it's one better than that. This Lego analogy is not quite right because you don't have strong bonds between the layers. There's no reason you have to have some particular alignment of the two layers relative to one another. And so, in fact, in these Moiré systems, or in these two-dimensional systems, what you can do is you can stack them and you can twist one layer relative to the other. Because there are no strong interlayer bonds, this is perfectly okay. You can see here, if you look closely, there is this extra modulation that you pick out by eye. This is known as a Moiré superlattice. And there's an associated length scale that I'm going to call A sub m that is dictated by the original lattice constant of the material, but also depends on the twist angle that you've twisted these two materials relative to one another. Now you have a new length scale in the problem. And with that new length scale comes the ability to control the physical properties of the system, and in particular, engineer new band structures that, for example, mimic strongly correlated. So poster child of this, of course, came about in 2018. It was magic angle twisted bilayer graphene, that if you just take two individual graphene sheets and you twist them by a so-called magic angle of about 1.1 degrees, then electrons can hop from one layer to the other, but as they're hopping, because there are changes in the local atomic registry between the two layers as a function of spatial position, it turns out that there's a particular magic angle where this hybridization gives rise to very, very narrow electronic bands right near the Fermi level. And anytime you have narrow electronic bands, it means that the kinetic energy of carriers is basically relevant compared to interactions between particles. And lo and behold, if you just measure transport properties of this magic angle graphene system, what you find is that if you half fill it, this mod insulating space that I talked about at the beginning, you get some insulating behavior. If you dope away from this insulating behavior, you can get superconductivity. And so at face value, this looks very similar to physics, for example, of high temperature superconductors. I think the analogy is imperfect, except that I think there's something deep about how electronic interactions are giving rise to interesting physics, whether it's correlated insulators or superconductivity. But there are many other examples of interesting states. Okay, so before going on, I want to just talk about, kind of reframe this a little bit and talk about two limits that you might consider for Moiré systems like I've described. One case is where maybe you have relatively weak Moiré potential modulation, and so the carriers that are moving through this periodic modulation just perturbed by it. And in that case, you still have some electron liquid, and in particular, if you apply a magnetic field, ends up happening is you get something known as a Hofstadter butterfly. So there's some interference between the electronic scale of the electronic modulation, the length scale, the magnetic length scale associated with the applied magnetic field. And what this does is it changes the energy spectrum of the material. So if you look at the energy of electronic states as a function of the applied magnetic field, what you find is that at low magnetic fields, this looks very much like what I talked about for the two-dimensional electron gas. You have a set of sharp peaks in the density of states. So this picture is showing kind of electronic states that are available to the system. So this is sort of your Landau level limit of Moiré system. But once you get to a high enough flux that you have appreciable number of flux quanta threading through each Moiré unit cell, and actually this spectrum gets quite a bit more complicated. It turns into there are additional energy gaps that appear in certain places, and it's self-similar, and it's actually a fractal energy. You might wonder, why don't you see this in regular materials? Well, of course, you have some atomic modulation associated with the individual atoms in any given material that you have. But if you go through the numbers, you find that you need a magnetic field of thousands of Tesla in order to get to this regime where you have an appreciable number of flux quanta. And for the theorists in the audience, that is not something we can do in a lab. On the other hand, this Moiré system, now the length scale is much, much longer. And so it's of order, say, 10 nanometers or so for typical systems. And then you can get, depending on where in this gray bound you are, you can get these either at the National High Magnetic Field Lab or maybe in your laboratory at your home institution. Now, These Hofstadter bands, you can see they sort of break up into a series of discrete bands. So I'm going to replace this image with a similar one that has some lines drawn up. So this also the axes are transposed. Sorry about that. So this is the energy axis. This is applied magnetic field. You can see as you apply a particular magnetic field, when you have half a flux quantum per unit cell, you have two bands. When you have a third of a flux quantum per unit cell, three bands. Fourth, you have count them there, four, and so on and so forth. And in the gaps between these various different subbands, there is an associated topological invariant. So these themselves are the subbands themselves have Chern numbers that give rise to quantized Hall resistance, just like you get in in a magnetic field. And typically in experiments, we don't control the energy, we control the density using a backgate underneath our two-dimensional system. And then these lines, these gaps follow straight lines in the phase space of applied magnetic field and the carrier density that you have. Okay, so that's one limit. Second limit is going back to this case where you have electron solids that are favored. So if this Moiré potential that you create by twisting materials is very, very strong and interactions are very, very strong, then actually your carriers will be localized in a particular spot in the Moiré unit cell. And this is known to give rise to things like Mott insulators, as I described, and also generalized Wigner crystals. So I'll say what those correspond to in a second. A Mott insulator, remember, corresponds to 1 electron per site of your lattice. That's what's shown here to the right. And in fact, you can actually image these sorts of Moiré systems. This is an STM image from Microscopic and Feng Wang that actually you see this sort of periodic modulation of bright, dark, and it corresponds perfectly to the known period of this Moiré superlattice. But you also get insulating states even when you have some fractional filling. So for example, if you have 1 electron for every 3 Moiré unit cells, then as long as long-range Coulomb repulsion is strong enough, still you want to form some sort of Wigner crystal. But now it's known as a generalized Wigner crystal because these electrons are pinned so that they sit at particular sites in Moiré lattice. And again, you can image that directly through scanning tunneling microscopy. And at 2/3, there's similar physics and you get a honeycomb lattice. So the specific lattice that you get depends on the filling. You can get stripes and other orders as well. And in fact, people can image things. Okay, that brings me to kind of what I want to talk about today, which is looking at a particular class of twisted two-dimensional materials known as transition metal dichalcogenides. So I'll tell you a little bit about how to think about these transition metal dichalcogenides. I'll also say something about what we use, a particular local scanning probe, to measure them. I'll show you a couple of examples of Moiré systems that we studied. One is a heterobilayer, where this is the same picture from my title slide, where we see a mixture of these two limits depending on magnetic field we apply and the carrier density. That is, we get both charge order and scatter states. And this actually can be understood thinking not in terms of the individual atoms that make up materials in this Moiré system, but rather treating each Moiré site as its own little Moiré atom. Not so little, it's hundreds of atoms that are associated with that. But nonetheless, the same sort of thinking about atomic orbitals can apply in that situation. Then I'll talk a little bit about another material system, twisted homobilayer of tungsten diselenide, where depending on the specific twist angle that we're looking, you get different ground states, which are in all cases strongly correlated. Interactions matter a lot in all cases. But in a certain range of twist angles and a certain range of displacement fields, we find that ground states are actually topological. And so I'll talk about that as well. All right, so what are transition metal dichalcogenides? These are semiconducting two-dimensional materials. Chemical formula is MX2. The metal atom can be molybdenum or tungsten, for example. The chalcogen atom could be sulfur, selenium, tellurium. And the structure looks something like this. If you look from the top down, actually it has the same honeycomb structure as graphene does. But now the two sublattices of this honeycomb structure are distinct. So one of them is made up of the metal atom, and one of them is made up of the chalcogen atom. Actually, things form sort of trigonal prisms. So there's two chalcogen atoms, one above and one below. You can see that. And so this thing breaks inversion symmetry. A lot of these elements are very, very heavy, so spin orbit coupling plays a big role as well. And all of this adds up to low energy band structure. It looks like this. So what I'm showing here is just the Moiré, it's just the Brillouin zone associated with a single transition metal dichalcogenide system. There's an energy gap between the valence bands and the conduction band. So it's a semiconductor, and these valence bands are split by strong spin orbit coupling. There are two degenerate low energy pockets for these valence bands, and I'll denote them as values K and K prime. And again, because of the spin orbit coupling, actually there's a particular spin associated with each of these values. So there is one quantum degree of freedom associated with this transition metal dichalcogenide. So just like the case of magic angle graphene, if you stack these transition metal dichalcogenides with a small interlayer twist, you get a Moiré pattern. Matters what sort of stacking you use. Actually, I'll only be talking about this AA stacking. And just like in graphene, if you calculate what is the band structure associated with this Moiré superlattice, you find that the bands can be very, very flat. So this is an example at degrees. The really nice thing about transition metal dichalcogenides, or at least one really nice thing about them, is that actually there's no magic angle. You get relatively flat electronic bands over quite a large range of angles from, say, 1 to 5 degrees at least, where the bandwidth can be order of 10 millivolts or less. Now, depending on what sort of transition metal dichalcogenide you start with, what chemicals you put it in, you can have very, very different physics depending on the stacking. You can have very, very different physics. As you're tuning this twist angle, you're changing the size of Moiré superlattice, and that means it turns out that you're changing also the on-site U and the hopping between sites T. And critically, if you so both of these are changed as you change the twist angle, but actually the ratio of them changes quite a lot. So as you're going from some twist angle, say from 3 degrees to 1 degrees, ratio of on-site repulsion to the hopping between sites grows larger and larger. The smaller you make your twist angle, larger and larger your Moiré unit cell size is. You can get, by going to very low angles, to this strongly interacting limit where U is much, much larger than T. And also, these systems, as I'll show you, are very, very sensitive to applied electromagnetic fields. So you have a tremendous amount of tunability also with these experimental knobs. Not everything is rainbows and unicorns for transition metal dichalcogenides. So these are semiconductors. And you may remember that if you try and put in a metal next to a semiconductor, you get something known as a Schottky barrier. That is, there's a barrier to ohmic transport. So it's very, very hard actually to make electrical contact to these materials. And that actually has limited quite a bit what sorts of regimes of phase space that one can explore, because this gets worse and worse. Lower and lower you go in terms of carrier density in your sample. And for a given Moiré unit cell area, this corresponds to kind of longer and longer Moiré wavelengths. That is exactly this most interesting regime where interactions are longest. So that's been a challenge. The other thing that the dirty secret of the, or maybe not so secret of the Moiré community, is that actually as we are making these samples, we pick up one flake at a time with some polymer stamp. This is sort of jiggly. You put it down, you press. It's some, you try and be gentle, but you have some uncontrolled strains and forces that you're applying as you assemble these samples. And so you can pick something up, twist to a target angle, put it back down, but what you get out may or may not be exactly what you wanted. And in fact, if you look even on scales of hundreds of nanometers, this is just one particular example from a scanning tunneling microscope measurement that can resolve this. You can see that the periodicity, the Moiré wavelength, is changing quite a bit. And that obviously is detrimental if you want to do some sort of large global transport measurement, for example, even if you can get the contacts. So this motivates using different measurement approaches, new techniques to try and get at these most interesting regimes and mitigate the problems of this spatially varying twist angle disorder. And my probe of choice is a single electron transistor. So you could think of this just as a small metal island or quantum dot that's separated by tunnel junctions, source and drain. And I just schematically draw the energy diagram. Well, as long as you make this quantum dot small enough and adding additional charges to it plus some large charging energy. There's some Coulomb repulsion with all the electrons that are already occupying this metal island. And what that means is that there's an energy gap between the highest occupied state of the island and the lowest unoccupied state. It's given by E squared over 2C. And if Fermi level of your leads is aligned such that it's in this energy gap, and if your temperature is low enough and electrons can't hop from the source onto the island, they can't hop from the island onto the drain, and so you get no conduction. On the other hand, if you have some state nearby that can electrostatically tune the energies of states within this metal island, you shift these states up and down, and you can come to a regime where it's possible for an electron to hop from the source to the island, then from the island onto the drain. And in this condition, you get conduction. So this together gives rise to a pattern known as Coulomb blockade. That is, current from source to drain has some periodic modulation as you tune the electrostatic environment of your island. And this is ultimately what we'll be using. Basically, this response is what we'll be using to measure the sample. How do we do it? Well, we evaporate aluminum onto a pulled quartz fiber. So this is an SEM image of what we do. We put this tip, which has the SET, right, the single electron transistor right at the apex of the quartz rod. We bring it close to the sample that we'd like to study. In this case, the sample itself is providing the gating along this x-axis that I was showing you before. What we can do is we can hook up a battery. We can apply a voltage to the sample that fixes its electrochemical potential, which is the sum of the chemical potential of the sample and electrostatic potential. And so the electrostatic potential is what the SET is sensitive to. And we also have backgate beneath the sample. As we apply voltage to the backgate relative to the sample, that changes the carrier density in the sample, that changes chemical potential in the sample. And because the electrochemical potential is fixed, there must be a corresponding change in the electrostatic component. And that's what we're sensing with the single electron transistor. And schematically, it looks something like this. If you have two flat bands, peaks in the density of states in your system that you'd like to study, as you're adding electrons one by one, when you're filling this peak in the density of states, the chemical potential doesn't change very rapidly. So you get a plateau in the chemical potential. As you traverse this low density of states, there's a jump in chemical potential. And then as you're filling this next peak in density of states, you get, again, a flat behavior. In practice, we often measure the derivative of this. That is, we apply an AC voltage to the backgate, and then the step in chemical potential turns into a peak in inverse electronic compressibility d mu dn. That is what we're sensing in our experiment. So any large signal that we see in our experiment corresponds to an energy gap, or more generically, a low density of states. Okay. So the first sample that I want to tell you guys about is a hetero-bilayer, which is composed of tungsten diselenide and molybdenum diselenide. Actually, this was the first system proposed by Alan McDonald and Fengcheng Wu as a really nice transition metal dichalcogenide system to look at for these sort of correlation effects. Now, there's a couple interesting things about it that I want to highlight. So first of all, these two compounds, even though they're different chemical compounds, actually their lattices are very close to match. And the Moiré wavelength is dictated both by lattice mismatch delta and also the twist angle theta. So heterobilayers, for most heterobilayers where there's a lattice mismatch, that means that as you decrease the twist angle, eventually this delta squared term in the denominator dominates, and your Moiré wavelength has some cutoff. You can't go past particular wavelength. On the other hand, for lattice match compounds, you're mostly dictated by theta, and so your Moiré wavelength can diverge and take you to a strongly interacting one. The other really nice thing about this hetero bilayer system is that if you calculate what is the Moiré potential that you realize in it, actually it's quite strong. So you get this nice triangular lattice of minima in the Moiré potential. That's where the carriers like to sit. And because these minima are so deep, this is of order 100 milli-electron volts, actually the electron wave functions are very, very localized within these Moiré potential minima. Here's our sample. Maybe the zoom in is more useful. I'll just tell you a couple of critical aspects of it. So first of all, the twist angle is about 1.35 degrees. It corresponds to a Moiré wavelength of about 15 nanometers, so actually quite large compared to what people have traditionally studied in transition metal dichalcogenide systems. And what we'll be doing is we'll be doping holes into the tungsten diselenide layer. So there's some band mismatch between two components of this Moiré superlattice, and because of the relative band alignment, as we dope holes into the system, they actually preferentially want to occupy the tungsten diselenide layer. So the molybdenum diselenide is just there to provide the Moiré potential, but otherwise it's a potato. I want to just flash this quickly, comparing what you see in transport across the device to what we see when we measure locally compressibility with the single electron transistor in a particular spot highlighted here in black. You can see there are some peaks that we observe in transport. If you were just to see these peaks, you have no idea what's going on. Look in compressibility locally, all of a sudden everything is much, much clearer. So I've labeled these with some numbers. I'll describe why in a second. But you can see there's a dramatic difference in the quality of data or how much you can resolve from a particular measurement. All right, so what do we actually see? I'm showing here is the color plot of inverse electronic compressibility as a function of hole doping, so number of holes per Moiré unit cell, applied magnetic field, locally at some spot that has a twist angle of 1.33 degrees. And in this picture, red corresponds to incompressible. That means that there's some energy gap in the system. And you can see at low magnetic fields and at low fillings between 1 and 2 holes per Moiré unit cell, there are a number of red features that are appearing in the data. There are these in the middle that have some fractional values. So these correspond exactly to the generalized Wigner crystals that I was showing you earlier. You have some commensurate arrangement of charge in your Moiré lattice that doesn't completely fill every single site. Now, something interesting happens when you increase the magnetic field. You can see these generalized Wigner crystal states weaken considerably, and now you start to see something which is slope. Finally, as you go to even higher density, you can see that actually most of the features that we observe, these incompressible red states, are sloped. There's a small region, I'll come back to this, vertical features again, but it's a complicated diagram. I'll go through it one by one. Basically, you can see that there is very, very different phenomenology that we observe as a function of kind of this phase space of magnetic field and doping in our system. And so each of these states you can label by 2 numbers. One of them is the Chern number of the state that is related to the slope that it has. And the other is the zero field intercept S. And all of these can be labeled by those 2 numbers. Anything vertical corresponds to a topologically trivial state. So these are like the generalized Wigner crystals, broken symmetry states in integers. Anything diagonal is a topological state. And in this case, these are appearing at high magnetic field. So these are just the Hofstadter states that I was telling you about before. And you can see I've sort of highlighted in different colors, different regimes of different behavior that we observe. How to understand all of these different behaviors? Well, the right starting point actually is thinking about the Moiré potential well. So these are very, very deep. These are very, very far separated. So you can think about an individual well, and we'll have some eigenstate associated with it. Lowest energy eigenstate is like an s orbital. And as I said, the charge is very confined in this s-like orbital because there's 2 valleys or 2 spins in the system. this is actually a twofold degenerate level. And because the wells are so weak, actually, there are additional bound states that behave as though they're p orbitals. These p orbitals are more extended. There's more overlap between them. This corresponds to a higher probability of hopping, that is, a larger bandwidth of the electronic band. So we just ask the question, you start from these eigenstates of quantum well at a time and allow them to hybridize to form a band structure in your Moiré system. What you find is something that looks schematically like this. So there are two s orbitals. One of them is occupied first, and then there's some large energy penalty u corresponding to double occupancy. Then these p orbitals give rise to more dispersive bands. So these s orbitals are very flat because there's very little overlap between them. The p orbitals, on the other hand, give rise to dispersive bands. And you have a choice. If you're filling first hole per Moiré unit cell, it's clear you want to put them in this energy band. But as you fill the next hole between 1 and 2, you can choose one band or the other. So as I've drawn it here, say you want to occupy this upper Hubbard band. Remember, this upper Hubbard band now has some opposite spin relative to the lower Hubbard band. These dispersive bands can have same spin. And so the relative alignment of these two possible bands to occupy is now dictated, for example, by the applied magnetic field that you have in your system. We can cook up a very simple picture for the free energy of the system, taking into account the original band offsets, some difference in effective Zeeman field, some kinetic energy associated with the dispersive bands, and some Stoner repulsion between different types of carriers. And if we just minimize this free energy and ask the question, what's favored in the ground state? What you get is a picture that looks like this. So low magnetic field and low filling in this red portion is favorable to occupy the opposite type orbital. So this regime here, you're occupying still the flat band. But eventually, magnetic field is large enough such that it's favorable to occupy a spin-aligned type orbit. And you start to fill these more dispersive bands at high magnetic field. So this is actually a transition from a spin singlet state on a particular site. So it's like a singlet state of a quantum dot to a spin triplet type state, again, with both spins on the same real space site, but occupying now different orbitals. If you go out here, again, once you've gotten to nu equals 2, if you just follow along your low magnetic field, you've completely filled both of the S bands. So now the only thing you can do is start to fill these P bands. These are more dispersive, and that explains what's going on in terms of the soft starter physics, that is, when you're occupying the flat bands, you tend to favor charge-ordered states. When you occupy the dispersive bands, actually you favor forming this Hofstadter type physics in a magnetic field. And then lastly, I mentioned there was this funny region here. There were a bunch of vertical states. Those, if you just look at where they occur, at the fractional values that they occur, it's actually the exact same fractions as we had over here, except modulo an integer. And what spit out from this very simple theoretical model is that actually in this regime, in this little purple regime here, you're occupying both bands. So if you just go from 11 Tesla and add the number of holes to your system, you start off, you're occupying dispersive bands, dispersive bands, dispersive bands until you hit this spot right here and you start filling states in this purple region. And actually you start to empty holes in the dispersive band and start to fill them in the flat band. And so you change this occupancy, and actually within this purple window, you have partial occupancy of both flat and dispersive bands. That is, you have both light and heavy fermions. We see these vertical features. So this is some sort of charge-ordered state, some sort of electron solid. Because they're vertical and not diagonal, it means that actually somehow cooperatively both these light and heavy fermions are crystallizing in some sort of electron solid. All right. That's all I really wanted to say about this. Again, let me briefly summarize, and I'll pause for questions if there are any. So we looked at this tungsten diselenide and aluminum diselenide heterobilayer, and understand it in the limit of Moiré atoms. That is, each Moiré site itself can be thought of as hosting some quantum well, which is like an atom, and you can tune depending on which type of band you're occupying. You can change the relative energies and therefore change preferred ground states. And actually, there are really interesting regimes of charge-ordered states that still we don't have a full understanding of what exactly is going on. So let me pause there if there are any questions before I go on to the next part.
Yeah, question. So things like a theta tends to be like a 1 degree or something. It could be a 30 degree or something.
That's right. So for this particular sample, it's heterobilayer. So all we could do actually as we were assembling this was look at the crystallographic axes of the flakes as we were picking up. So these things tend to be in strips, and so you can usually see some crystallographic axis. You don't know if it's a zigzag edge or an armchair edge. So actually there's you don't know which stacking you get for the heterobilayer before you stack it, but you try to come close to aligning these edges so that the twist angle is low, because it's at this low twist angle where the Moiré superlattice dominates. So the 1.33 degrees or something that order of magnitude for this particular sample was a fluke, but it's nice that it was in this low twist angle regime.
So just to understand, you want to have a scale separation. Right?
That's right. Yeah. The longer the Moiré wavelength, the stronger the interactions are relative to the bandwidth.
There's something here about the compressible states in between the various and what happens with the lower temperature?
So these are measurements done at, you're talking about the blue regions here, right?
Yeah, and maybe like between things.
Oh, like here or here. Sure, yeah. So those blue things, I'll tell more about them in the second half of the talk. So these are indicative of phase transition. So as you go from this spin singlet to the spin triplet, you can see there's this sharp blue feature. This is associated with a phase transition between two distinct electronic states. And similarly here, if you go to lower temperature, these sharpen up and you can see that they're associated with switching from this kind of Hofstadter regime to this funky charge order. All right. So let me just quickly move on to the last thing that I wanted to talk about. I think I don't have a tremendous amount of time. So in certain homobilayers of transition metal dichalcogenides, what you find is that the details of Moiré stacking give rise to something that looks more like a honeycomb lattice rather than a triangular lattice. So there are local sites that are quasi-symmetric that have MX stacking, that is chalcogen above metal, or XM, that is metal above chalcogen. And if you look in real space, there's actually a winding number, a topological winding that happens associated with some layer pseudospin degree of freedom. And that topological winding gives rise to a Chern index for the associated bands of this homobilayer system. And in fact, depending on what your specific twist angle is, it's been theoretically predicted that you get different topology out. And that can be controlled both by twist angle and by the applied electric field, which changes the relative energetics of these two different blocks. We wanted to look at this in twisted tungsten diselenide homobilayers. So again, this is the sample that we have. Twist angle ranges from about 1.1 to 1.6 degrees. That corresponds to a Moiré wavelength of about 12 to 17 degrees. So we have about a factor 1.5 change in Moiré wavelength that we can explore in this system. And when we measure it with our single electron transistor, what we find is that at integer filling, so this is blue is inverse compressibility. So a peak is some gap state. At integer fillings, we see peaks. That is, there is some energy gap opening up. Energy gap at nu equals -1 necessarily, again, is breaking this spin valley symmetry in some way. So this is a broken symmetry state. And in order to tell what is the nature of the insulating state that develops, what we do is we apply a magnetic field, just track how it evolves as a function of magnetic field. Any topological state should be sloped magnetic field like the Hofstadter states. And indeed, if we look at nu equals 1, as we increase the magnetic field, there's an incompressible peak. Sorry for the change in color scale. Red here corresponds to incompressible. It goes all the way down to zero magnetic field with a slope. This is a quantum anomalous Hall state, like I talked about at the introduction. Nu equals 2, we see something vertical. So the net Chern number in the state is 0. Nu equals 3, again, there's a diagonal feature corresponding to Chern number of 1. And at nu equals 4, again, there's something vertical. So net Chern number 0. So maybe in the interest of time, well, I'll just mention that we can do the same sort of mapping as a function of filling and magnetic field. Again, we see at high field some topological states. Again, you can see these sharp dark blue features that correspond to phase transitions, where the nature of the states changes abruptly. And basically, this defines a line where in the high field regime, we're fully polarized, like we talked about for the heterobilayer, and in the low field regime, we're partially polarized. And what that implies to us is that these Chern states correspond to first occupying a particular valley. They spin up, valley K. And at nu equals 2, we've occupied both valleys, and that have opposite Chern numbers. So that gives rise to a state with Chern number 0. Nu equals 3, start to populate again one of the valleys, and again we get a Chern state, and at nu equals 4, again we've canceled out that Chern number by populating the opposite spin valley type. So the nice thing about this sample, as I said, there's a variation in twist angle. So we can look as a function of twist angle, how does this topological behavior depend on twist angle that we locally as we move our tip to different spots over the sample. This is just the data that I showed you before. Again, there are these diagonal features going all the way to 0 magnetic field. If we decrease the twist angle, even by a very, very small amount, actually incompressible states at nu equals 1 are vertical. So the state has gone trivial, no longer topological. If we increase twist angle, even up to 1.31 degrees, again, you can see at nu equals 1, the state is vertical down 0 magnetic field. So we're changing the nature of the topology. There is basically a topological transition. You go from a trivial insulator at nu equals 1 to a topological insulator in a very, very narrow window between 1.2 and 1.25 degrees back to some sort of trivial insulating ground state. So twist angle tunes the tunes dramatically the behavior of the system, and similarly for the state at nu equals 3, it's really only topological in a very narrow. We can go one better. We can look at how the displacement field affects the behavior of the state. There's a prediction that there's a change from this symmetric case where you occupy both XM and MX sites to a state that's favored in the presence of a displacement field where you preferentially occupy just one of these layers. And we can use our tip to locally gate the sample. And in doing so can then effectively modulate the displacement field. So here, this is a picture at nu equals 1. As you increase the displacement field, this incompressible state gets weaker. And then past the critical field, it starts strengthening again. This sounds like the sort of displacement field-driven topological phase transition that's been predicted. We can do one better than that. So we can also look in a non-zero magnetic field where a trivial state with Chern 0 is just vertical, the topological state is diagonal, so the density at which it occurs will be different for what should be the trivial state at high displacement field, the topological state at low displacement field. Indeed, we see that if we just take cuts, high displacement field, at low displacement field, we see, yes, diagonal at low displacement field, state is vertical, high displacement field. And by doing this in multiple different locations with multiple different twist angles, you can build up a phase diagram of where the behavior is trivial and where it's topological. All right, so I think for interest of time, since I'm basically out of time, I'll skip this just to say that details of the relaxation of the lattice matter in terms of which topology is favored or not. And so after our result, actually, it was as you saw, the twisted homobilers were predicted to be topological over quite a broad range of twist angles, and we certainly don't see that. But taking into account these atomic displacements, actually, this was a calculation done with the benefit of machine learning, and they found at least Chern numbers of the bands that were twist dependent and consistent with our results. The last thing I want to just very quickly highlight is basically the role of what happens as you change the relative energies of these Moiré bands undergo magnetic transition. You can see at nu equals 2 and at nu equals 3, that's 2 and 3 holes per Moiré unit cell, there's abrupt change in the electronic behavior as you undergo magnetic transition. So this is saying that nature of the correlated states that you get out, or even compressible states, some of these are metal insulator transitions, depends very, very sensitively on the magnetization of your carriers in your system. But on the other hand, back quickly, you actually look at the same sorts of blue transitions. So this is now a different twist angle. You can see there's kind of a series of these blue streaks, we can use a Maxwell relation to go from the measured compressibility to the magnetization, and its change as a function of carrier density as we dope the system. And just by integrating along these particular lines, you can then understand how the magnetization changes. And we see that there are these abrupt drops as you go through these features here. So these are really magnetic phase transitions. We can say that with certainty based on our data in the Maxwell relation. And the last thing that I'll just highlight is that again, we can look and ask the question, how do these transitions depend on local twist angle that we're measuring? So here I'm plotting 3 different twist angles. Again, you can see in all cases, there's some blue features. These are the magnetic phase transitions. I'm plotting them not as a function of filling factor. Instead, now I'm plotting them only as a function of carrier density. And if you just mark off where are all these blue features, plot them on the same graph, you see that they all line up very well. And in fact, we've also measured monolayer tungsten diselenide. Those states as well undergo magnetic phase transitions, and you can see that the carrier density at which those magnetic transitions occurs matches really, really closely to what we see in the Moiré systems. So what this seems to be indicating is that at least for this range of twist angles, actually it's not the Moiré superlattice which is dictating where specifically the magnetic transitions occurs. Rather, it's the underlying material properties, that is the density in this twisted tungsten diselenide, which is telling us when you're going to be magnetic or not. And then that in turn has some huge effect in the nature of correlated states. So let me end just with a quick roadmap of kind of where we are and why I think still this idea of looking at Moiré systems is so exciting. So I showed you this picture earlier of various different types of topological phases. Of course, you can add interactions on top of it. So soon after the quantum Hall effect was discovered, these Landau levels are very, very flat bands. Interactions matter. And turns out you get fractional quantum Hall states that appear in a magnetic field. Very, very recently, it was found in a similar homobilayer system that actually there's fractional quantum anomalous Hall effect, not just quantum anomalous Hall effect in twisted molybdenum ditelluride. So that is the analog of this quantum anomalous Hall effect in the presence of interactions. Very recently, there was a report of evidence even of a fractional quantum spin Hall effect, which is the fractional analog of this one and has really no analog in the high magnetic field case that people have looked at before. So I think this is all very exciting. These states require spin valley symmetry polarization. The state would require actually no spin valley symmetry breaking. And so by choosing material properties, I think this at least gives a little bit of a motivation of like, where do you look in order to stabilize these most interesting cases? So let me end there with my conclusions. Again, I showed you this heterobilayer data where we can tune from charge order to Hofstadter states and various phases in between and understand it just as individual orbitals occupying quantum wells. And we saw that not only can you change kind of interaction strength based on the bandwidth, but you can actually change the nature of the underlying bands from topological to trivial, or at least nature of the underlying correlated states that develop. So I'll end there, and I'm happy to take additional questions.
Preferably from participants of other workshops first.
Have you guys found like a phenomenon that like you have no theoretical understanding of?
Yeah. Oh, I don't know what you mean by no, but so this little purple strip here is really, really weird. So you have a mixture of light and heavy bands. So in some sense, this sounds like Kondo lattice physics, like traditional heavy fermion compounds where you have local moments and itinerant conduction electrons, and there's some interaction between them. It's not that, because here all the spins are fully polarized, so you can't form Kondo singlets in this case, but nonetheless, you still have this coexistence of light and heavy bands. The degree to which they hybridize, we have no idea. What exactly is the nature of these states? Again, they're vertical, so that means you have a certain carrier density. It's partially heavy fermions, it's partially light fermions, and somehow together they are forming some commensurate arrangement of charge, some commensurate electron solid. How these are arranged, again, we have no idea what exactly is going on in that particular strip there. So That's maybe the best example. There are lots of things we don't understand, of course. And that's one of the most interesting.
Yeah, you showed a lot of nice examples where there's like electron-electron interaction and therefore correlations.
Yes.
There's interesting entanglement structure between things as well, or should I just think of these as classical?
In entanglement in a topological sense, or
Any sense.
so I guess I think one would indeed say that, you know, in order to stabilize the topological phase, there should be some associated entanglement between the carriers. I guess I don't know anything about, for example, the more traditional quantum entanglement. Let's say you have spins, and are these spins on individual sites, are they entangled with one another? My guess is probably not. And the reason why is because the systems that we're looking at here are actually the Moiré wavelength is very long. And what that means is that the exchange interaction, for example, t squared over u is very, very small, actually much, much lower than the temperature of our system. So any sort of spin ordering wouldn't happen unless we went to much, much lower temperatures, like a millikelvin or something. And so you should think of these states all kind of in the spin disordered limit or the paramagnetic limit. In the zero field case, when you apply a field, you polarize them all. So that's clear. There's a huge G factor in these transition metal like chalcogenide systems. But I would guess at least that because these are so far separated, then the entanglement between spins would be small. The details of exactly what the magnetic structure is not fully characterized, certainly in these systems and generally in Moiré systems. And it's an interesting question.
So one might theoretically have taken two of these Moiré material composite those with respect to each other to get even longer wavelength. Is that actually done?
Yes and no. Yes, yes. Rarely. So theoretically, it's very easy to wave hands like this. Experimentally, you have no idea how hard the students work to get to even one of these devices. So I would say each device, as you add one more twist angle, you add some power law difficulty to the device that you end up with. That said, several examples where people have stacked multiple layers. So, for example, I talked about magic angle graphene. Turns out that the same type of physics can survive if you stack multiple layers, 3, 4, 5, and people have observed interesting correlation effects and superconductivity in that series of samples. There are other interesting trilayer graphene samples also that we've looked at ourselves. There's even one experiment that I heard about in March meeting, which is the big condensed matter yearly meeting from APS that from Pablo Herrero's group, where they actually took 3 magic angle twisted trilayer graphene samples, separated them by boron nitride, put them on top of one another, and we're looking at superconducting transport in various different configurations. So it's really, really hard, and in a few select examples, people have done it, and it is also a really interesting direction to push.
What is the largest type of length scale that people achieve?
So this depends on the relative twist angle. So for example, I'll talk about the case that I know best. So for helical trilayer graphene, that means take a graphene sheet, twist next graphene sheet, then twist again by the same amount, next graphene sheet. There is a Moiré wavelength between top 2 layers and bottom 2 layers. And that is set by the interlayer twist of each layer. But then there's something called a super Moiré wavelength, which has to do with both of these twist angles. And that, instead of going as the lattice constant divided by theta, first order for low angles goes as lattice constant divided by theta squared. So to put numbers for a twist angle of 1.5 degrees, the Moiré wavelength itself, probably about 10 nanometers. Super Moiré wavelength can be several hundred nanometers. So it grows very rapidly. At some point, you may not care about that super Moiré wavelength, and that also is, I would say, still an open question. There are examples where that super Moiré wavelength does do important things, but I'm not sure it always necessarily has.
Pulling up on the first question about things that we don't understand. So you show the phase diagram for high temperature superconductivity. I still understand. Yeah. And this motivation. Yeah. So do you actually think this has anything to do with latency? What's your
Okay, so
listen to this particular?
right. I think my high level picture is the following. So for these transition metal dichalcogenide systems, Moiré wavelength is dictated by twist angle, and U and the T of, and also there's some nearest neighbor repulsion V, again, Coulomb interaction is long range. So there's that too, which may affect things. But as you're changing twist angle, you're changing Moiré wavelength, you're changing the relative values of these. So by doing these kind of angle dependent measurements, we're actually asking the question, for this physical realization, how does the underlying ground state depend on the parameters of this that extended Hubbard model that we're pursuing now? This is the honeycomb lattice, not a square lattice, which would be relevant for cuprates. There are proposals out there for systems that you might want to twist to try and get a square lattice behavior. And so I don't think there's a one-to-one relationship. Each material is different. I think at basic value, correlations are dominant, and you see similar ground states when correlations dominate, it seems like, based on what's been found in Moiré systems. Whether there's a one-to-one mapping, it's not clear, but maybe there's some insight into the Hubbard model physics.
So might be a weird question. Like if you take two layers and then make one of the layers rotate and change the rotational rates, is there any dynamic of this transition here?
I have no idea. So again, very easy to do things with hands and much harder to do things with experiments. So there are examples where people have rotated statically in a DC limit, I would say, to different twist angles, and you can see how the electronic properties evolve as you do that. I don't think any of those platforms is amenable to anything that would allow you to do some rotating frame physics at this point. My instinct is that would be hard because these things, although the friction is low, eventually there may be some sticking points. And so I would hesitate to tell a graduate student to try that, because that would probably be the end of this precious device that they made. But it's an interesting question.